Hello, I'm Steve Lyon. I'm a professor of electrical and computer engineering at Princeton. I'm standing in front of the micro-nano fabrication lab here that we use a lot in our research. In our lab, we are working on making quantum bits or qubits out of the spin of an electron, but have it to where we can have mobile qubits. And that has a lot of advantages for making the architecture for quantum computers. And a lot of the work we do uses the Cleanroom facilities here at Princeton. And in this video, we'll try and show you a little bit about some of the work we do and the kinds of experiments we've been doing.
This tool is the Heidelberg. This is what we use so that we can design our chips on the computer CAD software and then print them onto a little metal device. And this uses optical lithography in order to write those designs on the metal. There's a laser write head right here, and you mount your sample to this chuck here. It has vacuum holes so that your sample stays stuck to it. And then this will kind of raster scan underneath the laser, and it'll blank it or shoot it depending on your design and write your features down to like about a micron resolution.
We've decided to take a rather radical approach to making mobile but highly coherent spin qubits. We've done a lot of work looking at electrons in silicon. And silicon, we've been able to show, has wonderful spin coherence. And we've been able to show that we can have an electron spin stay in the same state for up to about 10 seconds. And to compare that, the actual time it takes to do a quantum operation with silicon electron spins is only a few nanoseconds. And so that works very well. The only difficulty is that if you try to move the electrons in silicon, because of the spin-orbit interaction, they lose their coherence very quickly, typically within a few microseconds. And so we're taking these new approaches to try and make spin qubits that are mobile but maintain coherence. And the physical system and that we're working on a lot is actually putting that electron spin into a vacuum. And the way we can hold it there in a vacuum is we have it bound. We have the surface of superfluid helium, and we can hold our electrons at the surface of the superfluid helium such that it sits just a few nanometers above the surface, but it's in the vacuum. And then we can use the chips that we make and various electrical gates to move this electron around wherever we want it. And we believe that from calculations, they say that these spins will stay coherent for tens of seconds, even when we're moving them around the chip. And so that's our goal, is to make these mobile spin qubits to figure out how to make a better quantum computer.
So we're going to go down to the etch bay and take a look at one of the tools we use to fabricate our devices. We grow all of our samples in the clean room here, and then in another section of the clean room we can use photolithography to write designs onto them. So right now I'm just going to mount one of our samples onto a carrier wafer. And this tool here is a reactive ion etcher. So we use this in order to eat away at the metals or underlying dielectrics that we want to erase so that we can create the devices that we wrote up earlier.
So this is an SEM, a scanning electron microscope, and it uses an electron beam to take images of our samples, and it lets us see very fine features. So this tool is actually equipped with a number of add-ons, including an X-ray spectrometer that we can use to actually determine the chemical composition of the samples in the chamber. And here I'm going to be looking at a sample fabricated in our lab using our direct write UV lithography system. And we can see this nice array of quantum dots and really characterize, for example, the size of these features as well as the chemical composition. So if I zoom out here, you can see this is a nice array of quantum dots. There's about a micron between the dots. So these are roughly 300 nanometers in diameter, which is a pretty impressive feature size for a UV lithography system.
Hi, I'm Emil. As you see here, we have an automatic wire bonding machine. So we make microscopic devices, and in those devices we have to connect different points and take electrical outlets from them. So this machine helps us to bond from a microscopic region to another microscopic regions. And we can do it automatically, much fast and precise way using this machine.
I hope that we've given you some flavor of the kind of work and the kinds of devices that we work on here. So thank you very much for letting us show you what we do here, and we wish you well.